So let's dive right in. There's 4 questions tonight, so it might take us the full time. So the first one is actually a geometry that hopefully you guys recognize from the previous tutorial. So we're told there's 3 identical charges. Each one has a charge of -2 microcoulombs, and they're on the vertices of an equilateral triangle. So this is the same as the equilateral triangle problem from previous tutorial. The side length is L of 8 centimeters, and we're asked to find what the charge density lambda is of the infinite line charge should run through the center of the triangle so the system is at equilibrium. So that's this charge right here. It's running perpendicular to the plane of the page, so you could think of it as going both in and out of the page. It's infinite, so it comes infinitely up out of the page, infinitely down into the page. And you guys might remember in lecture, there's kind of a derivation, and you can imagine that if you have this infinite line charge here, when you view it from the side, the electric field points outwards radially, but it looks like this from the side. From the top, it actually looks like this. So when we're viewing from a top-down perspective, the direction of the electric field is basically the exact same as for a point charge when we're working in kind of like a 2D example like we have here. So what we're asked to do is find out what this charge density is on this infinite line charge so that the system can be at equilibrium. The way that we're going to find out what equilibrium is we're going to pick a charge and we can solve for what the electric field is, where that charge is located. So that's the electric field due to other charges. And if that equals 0, then that charge, for instance, this one right here, it won't move because the force felt by a charge is equal to the magnitude of the charge times the electric field. And we can kind of argue through symmetry that if this charge feels no electric field, then the same will be true for all the other ones, and the whole system can be said to be at equilibrium. So putting that into words, maybe very quickly, just so we can talk about these a bit more specifically, I'm going to list as Q0, 1, and Q2, and I'm going to say for convenience that this Q0 is also, the position of that is where the origin is. So what we want to do is we want to find the electric field at the position, I'm just going to call this R0. We'll assume that means the position where Q0 is located. That's going to be equal to contributions from the first and second Q that we have labeled, Q1 and Q2, plus the electric field due to the infinite line charge. So I'm calling that E subscript lambda. And because we want this to be at equilibrium, we want there to be no force on this charge Q0. So this net electric field has to be equal to 0. Another way that you could think about this is write it as kind of the sum of all the electric fields at that point, kind of like the sum of the forces that we've done with Newton's second law last semester. So reminiscent of last week or last tutorial, these electric fields depend, for instance, from a point charge. I just draw it up in the corner here. The electric field of a point charge is equal to 1 over 4 pi epsilon naught times the charge times the distance squared in the direction of whatever the separation is between the point charge and where we want to evaluate the electric field. Similarly, for a line charge, it looks very similar. Geometry is a little different, so we have a 2 pi instead of a 4 pi, and we have a lambda over r instead of r squared, but again, it points in the direction radially outwards. So the point that I'm writing this down for is that the hardest part in all of these is figuring out what these distances and these vectors are. So we're going to proceed like we did last tutorial, and I'm going to do kind of painstakingly, we're going to write down what each distance vector is between these 3 charges and our charge of interest Q0. We'll write down what the vectors are, we'll write down what the lengths are, and then we'll write down what the vectors are. And then once we have that, it basically becomes plugging into the equations. It becomes very simple at that point. So I'm going to draw the three separation vectors between the charge of interest and the kind of the three that are producing the electric field. So we have R1, we'll call this R2, and this will be R lambda. And I'll go back and label these so we don't have to remember exactly what they're called. This is R1, this is R lambda, and this is R2. Because we went through this last tutorial, I'm going to maybe move a little bit faster than last time. We'll go through it in detail, but I might not work through all the geometry explicitly. If there's a question about something, please type it in the chat and we can do it if there's time. But if you guys are watching this after the fact and there's something confusing, I'd advise you to go check out the last recording because we do basically the same thing. Okay, starting with the vector, starting at charge 1, going to charge 0, we'll call that R1. It's equal to the length of the triangle because it just goes along the bottom here. And it goes from right to left, so that's in the negative I hat direction. The length of this is pretty easy to just pick out. I'm not going to draw the arrow symbol, which is denoting a scalar quantity, aka the length. It's just L. And the unit vector associated with R1 is just minus I hat. So I think as you guys get more familiarity, it'll be really easy to pick off. Like notice the way I wrote the vector R1 here on the left. You can identify what the length is. You can identify kind of these two pieces that make up the unit vector. It's all kind of pretty straightforward. So R2, the thing that I'm going to keep in the back of my mind is that the angle right here that forms an equilateral triangle is 60 degrees. So I'm going to say that this has length L, and the unit vector should be root 3. No, that's incorrect. It'll be 1/2. I hat, it's going to the left and down. So we have two minus signs. From this, we can easily pick it apart. The length is R2 is equal to L. The direction, kind of just decompose what I wrote on the left. It's minus 1/2 I hat minus root 3 over 2 J hat. And when I said I was keeping the fact that this angle is 60 in my head, notice that the sine and the cosine, oh, I missed up my 3. The sine and the cosine of 60 end up being some combination of 1/2 and root 3 over 2. The one that's a little bit more tricky, where is the line charge located? So that's our lambda, or what is the distance from the line charge to Q0? So this one, maybe I'll quickly get rid of what we drew before. And to note just this part in here, this little slice, this is 30 degrees. And what we would find out if we did this kind of painstakingly is the length of this is L over root 3. And because this is in the 30-degree direction, we have, instead of 1/2 and root 3 over 2, we have root 3 over 2 and 1/2. So I don't expect everything I've written, at least in the left column, to make perfect sense on the first pass through. If you guys want, we can go over it at the end. But I think if you guys go over the last tutorial video, it'll be crystal clear. Oops, this is our lambda. And the direction. Okay, so we have everything we need. Really the only reason why I wrote down the quantities in the first column is so that we can kind of decompose them into the lengths and the directions. The lengths and the directions, if we kind of re-examine what we have here, are the key quantities that go into the electric field. If you're worrying about the electrostatic force, those are the quantities that go in. We don't really need to deal with this vector explicitly, but I think writing down the vector is pretty helpful when you want to figure out what the length is and what the direction is. You can possibly work without it, but I think this is most straightforward. Okay, so let's kind of work with the equation that we've laid out up here and actually fill in values for it. So this is the electric field that we're trying to solve for at Q0. The net electric field, we already said that has to be equal to 0. So electric field due to charge 1. Charge 1 is a point charge. This is kind of like the field version of Coulomb's law. We don't have the second charge. We have Q1 over R1 squared times R1 hat. So that's our electric field from charge number 1, or the charge that we've labeled number 1. And notice that I'm just adding these straight up, we're just summing them, and any kind of directionality and any negatives are going to come about from the unit vector here. So charge 2, also a point charge, has charge Q2, we'll replace that in a minute. The distance is, we'll call it for now R2, and the direction is R2 hat. And lastly, we have that line charge right in the middle. The charge density is lambda, that's in units of coulombs per meter, or some version with some metric prefixes like microcoulombs or nanocoulombs per centimeter or something like that. But overall, it's the amount of charge per unit length. The distances are lambda, and remember, we don't need to square this one. And the direction of that electric field is in the R lambda hat direction. So this is everything we need. We can start filling stuff in, but before I do that, I'm just going to do a quick simplification or whatever. Imagine that we took this equation, it's 0 on the left side. We multiply both sides by 2 pi over epsilon naught, so that will cancel out this term. This term will be left with 2, and this term will be left with 2. So that automatically makes things simple. We don't have to worry about the pi's, the epsilon naughts. And now we'll start to fill in everything that we had from above that we've already kind of laid out nicely. So it's still all equal to 0. We have that 1/2 left over that we just kind of created. Q1 and Q2, we labeled them Q1 and Q2 so that we refer to them uniquely, but they both have the same charge. That's just lowercase q. It ends up being -2, but I'm not going to deal with what it actually is. We'll just call it Q for now. So it's Q. The length of R1 is L, so this denominator in the fraction just becomes L squared, and the unit vector is -I hat. So that's our first term. Moving on to the second, we have the same 1/2 that we just kind of created here. Again, we have Q over L squared, replacing Q2 and R2 respectively. And then R2 hat is -1/2 I hat minus √3 over 2 J hat. That's our second term. And lastly, the third term from the infinite line charge, we have lambda over L. This would really be L over √3, but 1 divided by L over √3 is just the same as saying √3 over L. So that's replacing R lambda, and R lambda hat is minus 3 over 2 I hat minus 1/2 J hat. So now at this point, this is just algebra. We've subbed in everything we need. I don't think there's any more. There's no more geometry. There's no more physics. We just need to kind of work with getting this. And what we want to solve for, in case we've forgotten, find the charge density lambda is what we're asked to do. So that's right here. The other thing that we can do, and we need to keep in mind, it's not a can do, it's that we need to do. We have terms in I hat, and we have terms here J hat. And I hats and J hats, you can't add like 2 I hat plus 3 J hat can never be combined any more than it is there. You can't you can't combine something that's multiplied by a J hat with an I hat. They will remain separate. So the point of this is that we need to move forward, and what we have is we have a vector equation here. We can solve this in the X components. It'll give us an answer. We can solve this using the Y components. It will give us the same answer. If we look at what we have here, our first term has an I hat, our second term has an I hat and a J hat, and our third term has an I hat and a J hat. So if you're keeping count, that means that there's only two j hat terms, which means getting to the answer via the y components is going to be less work. So I'll just make note that we're going to group we could call them the y components. We could call them the j hat terms, something like that. But we're going to move forward with the y components. You guys on your own at home, you can go ahead and verify that we get the same answer with the x components, but we will. This is just the simpler way, so that's the way I'm going to choose. So let's rewrite. This time we're only going to write the y components. So the first term contributes nothing. The second term, we have kind of this prefactor right here that I've written. And then we want the y part. So the y part is minus root 3 over 2. Everything here has j hats. We don't really need the j hats anymore. I'm just going to ignore them. We have root 3 lambda over 2. That's the bit out front. And for our third term, the j hat component from the unit vector is minus a half. So this is everything. This is now our simplified equation, and we just need to solve it for lambda. So, I made a little bit of a copying error. This is not a 2, that's an L. So what we have is we have an L. I'm going to cancel a few things right now. We have a half here, we have a half here. We have root 3 here, we have root 3 here. We have a single factor of L here, and then we have squared L's right here. So I'm just going to get rid of the exponent there. And what we're left with is 0 is equal to Q over 2L. Oh, and we can also cross out the minuses. Plus lambda. In other words, lambda equal to minus Q over 2L. So that's the entirety of it. So Alex had a question in the chat. You're focusing on the j hat component because the question said the line is vertical. No. So the line is vertical in the sense of, if you imagine the paper or the screen or whatever is sitting flat on your desk, it means that the line is coming out of the page. And it means it's vertical in that sense. It really doesn't matter if you rotate everything and you're lying on your laptop and your laptop's on the side, and therefore the line chart is horizontal. That's not really where the y hat and the j hat comes from. So we have, here's our coordinate axis that kind of just tells us automatically what j hat and what I hat is. So j hat and I hat are both in the plane of the page. Realistically, if you want to say what is the vector coming out here, this would be k hat, like the z direction. The reason I'm choosing the y component or the j terms or whatever you want to call them at this step right here that I just put the star at is simply because there's fewer terms. So what you could do is you could solve this a second way if you group the x components. You could have at this point, separate line of solving. What you would get, if we go really quickly, is we would just have 1/2 q over L squared. That would have a -1 from the I hat. 1/2 q over L squared. This would have a minus root 3 over 2. No, it wouldn't. It would have another -1/2. That's from this right here. And then from the line charge, we would have root 3 over lambda. That would also have a minus root 3 over 2 because we're dealing with I. Okay, so this is what we would have. This would be a second equation that would lead us to the same point. You can imagine ... We get down here and we would arrive at the same answer. The only reason I chose the first method is because here you have 1, 2, 3 terms, and algebra with fewer terms is simpler in my mind. That's literally the only reason. But it would get you to the same point. Okie dokie. So one kind of check just to make sure that everything is sensible, and I think you guys are probably getting pretty familiar with this. these three charges here, these Qs, they have identical charges, whether they're positive or negative. It just so happens that they're negative in this problem, but because they're all the same sign, we know they're going to repel. So the answer, which is kind of asking us, what is this charge in the middle that we have to add to bring everything to equilibrium? It has the opposite sign. So this is important because there's a bunch of repulsion going on, and we want to add in something that contributes attraction. So we want to stabilize the repulsion. That could only happen if we had this lambda end up with the opposite sign charge. So as far as a very basic check of did what we do make sense, yeah, we did a great job there. That answer seems reasonable. And if you guys want an actual number, like the microcoulombs are here, the centimeters are here, that kind of stuff. If you guys want to convert microcoulombs into coulombs, centimeters into meters, that kind of stuff, you can get an actual number for this if you so desire. Okay, problem 2, we have an electron gun. We're told it's composed, this is kind of the diagram for it. We're told it's composed of 2 oppositely charged parallel plates. There's a separation of 1 centimeter. I'm going to call that lowercase d. A heated filament provides electrons which wander through a hole in the negative plate. If the charge density on each plate is 50 nanocoulombs per meter, this should be meters squared, so this should be superscript. What is the speed of an electron as a fraction of the speed of light after it passes through the hole in the negative plate? And assume the diameter of the plates is much greater than the distance between them. So a few details here that might need a tiny bit of extra explanation before we go. So this filament is just a piece of metal. When metal gets hot, electrons come out. That's this kind of indicated part of the trajectory. They have no real significant velocity, so what we're going to assume is kind of at this side of things, v is equal to 0. That's kind of implied by this, what's the phrasing here? Wander. Yeah, so it's not really moving with any appreciable initial velocity. We're just going to assume the initial velocity is 0. The electron has a negative charge. The quantity of charge is E, the sign on it is negative. It's repelled by the negative charge distribution on the first plate. It's attracted to the positive charge distribution on the second plate. Or another way of thinking about that is there's an electric field in here which points from positive to negative. And negative charges move from high field, or they move kind of opposite the direction of the field. So what ends up happening is this electron picks up some speed, it accelerates because there's a force on it, and it ends up with some velocity v that is no longer 0. It's greater than 0. So that's what's meant by an electron gun. By the time the electron emerges on the left side, it's emerged with some velocity. It's been accelerated. Okay, so this is a fairly straightforward problem. Basically, what we're going to do is we're going to leverage the, there's many different ways you can solve these problems. I'll state first. What we're going to do here, maybe you guys can find a simpler way, is that the work done on the electron will cause a change in kinetic energy. And that work is just equal to F dot D. And the kind of the requirement to keep in mind, because there's going to be cases where you can say the work is F dot D, and then there's times you have to do an integral. This is true if F is constant. If you have a situation where F is changing, then you might have to find another way to solve this. So what is the force in this case? Actually, answer 2 questions at once before we go to the next line. What is the change in kinetic energy? Well, it starts with V0, so it has no initial kinetic energy, and it ends up with something with a non-zero velocity. So normally we would write something like 1/2 mv squared final minus 1/2 mv squared initial, but we can agree that mv squared initial is 0. So I'm just going to replace the delta ke with 1/2 mv squared. That's our final velocity. There is no initial velocity. Okay, so FD is akin to saying QE, right? If there's an electric field, the force felt is the charge times the electric field, dotted with D. And I've been extra careful to write down the vector signs and the dot product and stuff like that. And I'm going to stop doing that. And I think you guys have to find the way that is best for you in how you want to solve this. So you can be very careful. You can say that, for instance, you can say that Q is equal to minus E. And you can say that the electric field is equal to whatever magnitude it is times I hat. And you can say that D, which is the distance that's traveled, is equal to magnitude D in the I hat direction. And you can keep track of these signs the whole way through. And what you will find is compute the dot product with the vectors like I've done here. And you have 1/2 mv squared is equal to electron charge times the magnitude of the electric field times the distance traveled. So you have these two negatives that end up canceling out. So if you want to be really careful and you want a foolproof method, you can stick with vectors, and I'd recommend that. But it can be a lot faster, and if you have a good grasp of the situation, you can dispose of these, and you know that this is going to be QED. You can worry about the signs later, and you can ask yourself at the end of the problem, should my answer be greater than 0 or less than 0? And I find that can be a faster way to getting to the answer. And it also kind of helps you fact check if it should be positive or negative and make sure you understand what's going on. So let's assume we had done that and we were kind of moving forward from this line here. So we want to figure out what is the speed. We're pretty much set already. So we're going to solve for V and do a few other things along the way. So let's just leave V squared here. We'll have twice the electron charge divided by the mass, and this is the mass of the electron. And a lot of times in these questions and in physics in general, you'll have the ratio of the charge to the mass or the mass to the charge of an electron being a very important quantity. Because the mass of the electron is such a special number, I'm going to put a little m subscript e there just to make sure we know what mass we're talking about. Okay, so I brought the 2 and the m over. The electric field of a pair of parallel plates is just sigma, which is the charge density divided by epsilon naught. If we had only had a single plate, we would have sigma over 2 epsilon naught, but they add. The other thing to keep in mind is that this said the size of the plates is much greater than the distance between them. That's a requirement for us to treat these as infinite plates. If we didn't have these treated as infinite plates, then we can't use what I just wrote in for the electric field. And then we have the distance traveled by the electron in the vicinity of the electric field. So that's this D, the separation between the two plates. So what we're left with is V is equal to 2E, which is the electron charge, divided by the electron mass, times sigma over epsilon naught times D, all square rooted. And this is in variable form or in without actually solving anything explicitly. That's our answer. We're solving for a speed. Does it make sense if our answer is greater than 0, less than 0? Well, of course, greater than 0. It's just a speed. There should be no numbers under the square root here that come out as negative. These are just kind of standard checks you need to perform. But also, as I discussed, we kind of showed what this would look like if you had two vectors and they would get filled in here. So we knew that this was going to come out positive anyway. We didn't need to perform this check. Now, the last thing we need to do is deal with this kind of nasty detail here that says we want to express the answer as a fraction of speed of light. So I don't know if you guys are familiar with the speed of light or not. The speed of light is referred to as c, so 1c, i.e. 1 unit of velocity measured in speed of fractions of speed of light is equal to approximately 3 times 10 to the 8 meters per second. Really fast. So what we can do is if we have our answer, V, and that's in units of meters per second. We can just multiply it by a conversion factor. We want to end up in units of C. It's not an E, that's a C. In 1C, there are 3 times 10 to the 8 meters per second. So now we have kind of these meters per second were in the numerator here, they're in the denominator here. What we're left with is the same velocity, which is in units of C. So effectively, the answer of what I'm trying to get at is you want to express this as the question is written, you would just take the final answer and you divide it by 3 times 10 to the 8. So that's it, pretty simple. Geometries like these are really, really nice because the electric field is just pointing in a single direction. It's homogeneous, it's the same magnitude everywhere. So suddenly we can solve this with minimal involvement of vectors. We don't need to like draw out separations and all that kind of stuff. So I think you guys will find that some of the problems will get a little bit simpler in the electrostatics unit from here on out. And this is kind of the first one of that type. Okay, so next question here, our third one. We have a particle. We're told that its mass is 1 microgram. I will probably follow a similar trend and not actually solve this in real numbers for you guys, so the 1 microgram is not so important. It's going at 200 meters per second, and it's entering this square that's shown here in the dotted region where there's a uniform electric field. So it points downwards, and it has a magnitude of E. This magnitude ends up being 50 newtons per coulomb. If newtons per coulomb looks strange to you guys, you may have also seen it expressed as 1 volt per meter, but I don't expect you've seen this yet, but these are perfectly equivalent units, and if you break them up into kind of the fundamental SI unit building blocks that they comprise them, it ends up being the exact same thing. But just in case you've seen electric field as volts per meters, don't think that this newtons per coulomb is an error. They're the exact same. Okay, so we have this uniform region of electric field. I'm going to call this side length L. Suppose the side, yeah, so we're told that L is 20 meters. And we're also told that the particle exits the region and has been deflected to an angle of 35 degrees. That's shown over here on the right-hand side. If that's the case, then what is the charge? So what this really means is that the tangent to the trajectory right here is at an angle of 35 degrees with respect to the horizontal. The tangent is the same as saying this is the velocity, and if this is 35 degrees, what we can do is we can break this up into an x component and a y component. In other words, what we're going to start with here and keep in mind, but I don't think we're going to use till near the end, is that if you take tan of 35, that equals the ratio of the two components that make up the velocity. So what has happened here? It's kind of worth discussing. Initially, the particle started, had some velocity. We'll call this VI. And we'll give it a vector symbol. And if we wrote this in terms of components, we could say that VI was equal to, we'll call it Vx in the I hat direction. And if we want to be perfectly accurate and complete, we'll put a J hat and an I hat axes here so we know how to orient ourselves. Then what happened is it was moving to the right, it had this initial velocity, and as it entered the field, it felt the force. There seems like there was a charged force, there's a vertically applied electric field, points downwards, and what came about was a little bit of y velocity, more acceleration, kind of more acceleration. It made this growing component of y velocity until we finally left the region of electric field and ended up with a final velocity that had unchanged x velocity. And I'm asserting this, I'm not kind of proving it, but I hope you guys will agree. And we had this new Vy. So the reason I'm asserting that Vx is unchanged is because the electric field is applied vertically, and we know that the force on a charged object moving in a field is equal to Q E. So if E is vertical, then the force can only be vertical, and therefore the acceleration, which affects the velocity, can only be vertical, or in other words, all these things have j hats when we write out the vectors. So we've had a change in velocity, the y component of velocity. That's equal to, if we just think back to kind of first month of last semester kinematics, that kind of thing, that's equal to the acceleration in the y direction times the time interval over which the acceleration is applied. And maybe I'll replace this immediately because we know that the change in velocity, if we just did Vy minus, or final minus initial, we know initial is 0. So we'll just write down the final term, kind of like we did in the last thing with the kinetic energy, the last question. Okay, so what we can write now is that what is the acceleration? Well, that's equal to the force divided by the mass. Newton's second law, F equals ma, we've just reworked it here. Is the time. So the time is how long the particle spends in the region of electric field. And because it enters on a vertical side and it leaves on a vertical side, this is determined entirely by how fast it's moving in the x direction. In other words, what I'm saying is this traverses a horizontal distance L and is going a speed Vx. So it takes L divided by Vx amount of time to get through that region. So I think we're basically set here. I'm going to solve this in the way just to show you guys a different, remember I discussed here, we can do things out in vectors and it'll be explicit and we'll have to be very careful that we'll get the right answer, or we can kind of just work with scalars and get to the end and ask ourselves if the answer makes sense. So I'm going to do the second option for this one. So notice here that I've written F as just a scalar. I'm just going to say that the force is equal to QE. We have the length L divided by mvx. And what is it exactly we want to solve for? We want to solve for Q, I believe. Yeah, what is the charge of the particle? So let's solve for Q. Q is equal to mvx vy divided by EL. We don't know what Vy is, but we have this handy relationship up here with the angle that is going to help us with that. So if we solve that for Vy, we can make the substitution that Q is equal to m Vx squared tan 30, or tan 35. So what I've done is I've replaced Vy with Vx tan 35 divided by EL. So this is kind of our final algebraic answer. Everything on the right-hand side is a magnitude, so what we'll get out on the left-hand side, aka the charge, is also a magnitude. And up to this point, we haven't really had to think very hard about what direction is the field pointing, what direction did the charge move, what could the possible sign of the charge be. But now we need plus or minus. So I think we can pretty much examine this the figure we have here and deduce without any kind of extra diagrams, any extra like hard thought, that kind of thing. The electric field points downwards. If the charge was positive, it would be pushed downwards. The force would be downwards. Notice that the trajectory, the y velocity increases upwards. So I guess what I'm getting at is if this was a positive charge, we would see something like this. We see something the opposite like this. We see the charge moving in the direction opposite of the electric field, so we know that this is minus. So we know that it's this guy, and we can kind of just at the very end slide a minus sign in the front there. And that takes care of everything. So just a kind of an example of how if you have a good grasp of the situation, you can perhaps get a quicker answer without having to stress over 3 different vectors, how are they all lined up, one comes in where, that That's just my personal opinion. But now I've shown you kind of both sides of the coin. Okay, so I think this is our last question. Again, it'll be pretty similar. We're told a proton. So proton, instead of, it's kind of like the opposite, sort of an electron. So it doesn't have a charge minus E, it has a charge positive E. It has much more mass, which is important to keep in mind, but as far from a purely electrostatic standpoint, it's kind of the opposite of an electron. So we're told it has a kinetic energy of 4.11 mega electron volts. So I expect this is kind of a new unit, and we might get exposed to it in the next weeks, but I would be surprised if Professor DeVet's gone over what a mega electron volt is at this point, if he's going to at all. So we can talk about that before we really dive in. It's just another unit for energy. So basically the way to read this is we have a proton, some energy, kinetic energy. It's fired perpendicular to the face of a large plate that has a uniform charge density of sigma 2.7 microcoulombs per meter squared. We're asked what distance should the proton be fired so that it stops at the surface of the plate. So what we have going on here, so we have a large plate. It has charge density sigma on plate. We have a proton that kind of starts some distance away, and it ends up some closer distance to the to this charged plate. So what this means is it's moved. We'll call it the vector D. We could also label while we're here. It'll change to R's, but this is a vector between, or maybe not a vector, just the distance between the initial position and the center of kind of the plate. I'm going to call this, we'll call this L initial. This was the initial separation or the initial distance, not a vector, just the distance. And this was what ended up being the final distance. So the proton, the way that I've drawn it, you could draw it any which way you want. We haven't been told how this is going to work. I've drawn it moving from left to right. You could have it moving vertically. It won't change anything whatsoever. Okay. So I think this is a good drawing of what's going on. The only other details to add in is that this has some sort of initial velocity, initial speed. The speed is going to be greater than 0. This is just the magnitude. This doesn't imply the direction, although it is moving to the right, because we could add that in. And at this point, what's happened is the push from this field, or from this plate, is pushing to the left. It's pushed on it enough that it's kind of converted away all the kinetic energy, and the velocity is equal to 0. It's worth noting this is only kind of a momentary configuration, as the push or the repulsion that has kind of stopped the proton from moving to the right. In the next instant, it's going to push it back to the left, right? So it's going to kind of, you can imagine it's going to come into the right, and it's going to end up turning around, something like that. But we're just examining it, kind of, we're stopping at that moment right there where it's instantaneously stopped. And again, there's a few other ways to solve this from what we're going to do. You guys are going to get tools to solve this in coming lectures in ways that are easier than what we're doing right now. Okay, so we have some sort of kinetic energy that's going to change. That's going to be due to some sort of the force from this charge plate. So that force is going to be equal to QE dotted with D. Or in other words, we can kind of proceed as I suggested. The change in kinetic energy is going to be negative because it's going to end up at 0, not start at 0. D moves to the right, E is to the left, the charge is positive, so we know we'll also have a negative over here. The charge is E, the field is sigma over epsilon naught. And this distance d is actually, based on how we labeled things, if we want to figure out what the magnitude of that is, it's actually the initial is Li minus Lf. Notice that Li is bigger than Lf. So for that just to be a distance, the magnitude has to be the difference in that order. So these go away. And what are we solving for again? What is the distance? Yeah, so the distance is this quantity right here, this Li. So that's what we're going to end up solving for. So I think at this point it's basically algebra. Oh, actually, we're dealing with energy that's just kinetic energy. It's just provided in units of energy. It's not provided kind of hidden as velocity. So in here, where I wrote 1/2 mv squared is not necessary. I'm just going to call this Ke and give it a subscript I for Ke initial. So now this is just algebra, I believe. We had a quick question. Yeah, John saw that I missed a factor of 2, so you're totally right. That was kind of autopiloting. If you have one plate, E is sigma 2 epsilon naught. If you have two plates, you get to double it. They kind of just add up. It's really so it's sigma over epsilon naught. So this is what we used previously with the electron guns. This is kind of what I had in my head, not what we have going on here. This is what we want. So thank you, John, for catching that. Okay, so we've got the correct electric field in here now. We've got the distance, changing distance. Okay, we're just algebraing, and we're doing algebra to find this guy. So we have, what are we going to end up having? Well, 2 epsilon naught times the initial kinetic energy divided by sigma times, this is E, and one thing to keep in mind, I kind of implied it up here where I said plus E. You guys have a value for E, and I think it's like 1.602 times 10 to the, I'm just guessing or grasping here, but it's I think 10 to the minus 19 maybe. E is a positive quantity. It's just a constant, it's a number. If you have an electron, the charge is equal to minus E. If you have a proton, the charge is equal to plus E. But E itself is positive. So when I write E here, it's just a number, 1.602 10 to the minus 9. Plus LF is equal to LI. I think that's everything. That's the distance from which we want to fire the proton. This Li tells us how far away we need to do that so that we end up with LF being what we need it to be. So in this case, we want to stop at the surface of the plate. Okay, LF ends up being 0. Perhaps I could have made this a little more simple if we had figured that out from the start. This is more, I guess, more of a robust solution. If you wanted this to be 10 centimeters, if you wanted it to be 5 meters, you would just plug that in there. But we're plugging in 0 in this. Okay, so the other thing I want to talk about before we're done, this is the last question, but just so you're kind of not the first time you're seeing it, or give you a little preview, what the heck is this mega electron volt thing? So a mega electron volt, breaking it up first, 1 MeV, the mega is just a metric prefix. So first and foremost, that's equal to 10 to the 6. That's what mega means, electron volts. But still, what the heck is an electron volt? So an electron is just the energy that is obtained by moving an electron, which has a charge minus E, through a potential difference. And you guys may or may have seen, I don't know what lecture you're on exactly, but you may have not seen potential difference yet. It's the energy you get from moving an electron through a potential difference. So the equation that you may not have seen yet is this one. I'm gonna call this U. I think that's what you guys use. U to denote energy, because E is confusing because it also denotes electric field. So you take a charge and you multiply by a potential difference. So what I'm saying, this unit of energy that's called an electron volt is equal to a charge of 1e times a potential difference of 1 volt. Volt is the unit of potential difference. And as we kind of wrote over here, which is kind of convenient, one elementary charge, denoted variable E or whatever, or quantity E, is 1.602 times 10 to the minus 19, I think. I'm not sure on the exponent. I kind of just working from memory. Coulombs times 1 volt. When you multiply coulomb times a volt, you get a joule. So it's actually equal to 1.602 times 10 to the minus 19 joules. So if you were actually going to do something with this, try and figure out what this equation is with your calculator. Electron volt is not an SI unit, so you would need to convert this. It would be a pain, it would be annoying, but there are branches of physics in which the electron volt is a much, much, much more convenient unit. So that's why it exists and why perhaps it's being introduced here. But yeah, so 1 electron volt, same as, basically you use the same conversion for E to Coulomb, same as EV to joules. So that's how you would do the conversion. So hopefully not something you have to worry about too much, but now you've seen it, and it's also a good preview for when you guys get into potential difference and electrostatic potential energy. So I think that's all I have for you guys tonight. I'll hang around for a couple minutes if there's any questions. I see there's only a few of you, and there haven't been many questions throughout, but like I said, I'll stick around for a couple